Okay, everyone. Hey, Diego.
Hello, everyone.
Hey, Diego, I'll open with some introductory remarks. Is my screen big?
Mm-hmm.
Okay. All right. Well, as usual, here are the different ways to join us. Take a snapshot of this if you want. But the core is Discord. That's where you can find out everything. We are doing lots of research, so anything interested in a wide range of things, have a number of different threads, lots of people working on different things. Let you digest some of this. So let us know if you want to do something with us. This is a project we're looking for folks on, especially systems folks, PL folks. Okay. Also presenters, especially for classic papers. Doesn't have to be one of these, but these are some ones we think are important. And other ways to get involved. We're hiring. We give startups a way to just make themselves visible by giving a talk for free. And also, of course, volunteers and donors always welcome. Okay. Let me just mention today will be the last day of our format so far, which is 1 hour followed by 30 minutes Q&A. Starting next week, we're gonna make the whole thing 1 hour, have a presentation be 30 or 40 minutes, Q&A be the rest of the time, and then hopefully our speaker can jump on Discord for 30 minutes or less and answer questions. Okay, so be easier to give a talk and less time commitment for viewers. Part of the reason, by the way, we thought this might be a good idea is many conferences, really no such thing as a 1 hour talk anymore, unless you're a keynote presenter. So whatever talk you may have had for a conference, this allows you to potentially just use that. Okay, and without further ado, we have Diego here today. Welcome, Diego.
Thank you.
He's a PhD student at Mila, and you can find out more about the papers. You can read the papers through these links. Check out his website, and we'll send this out on Discord. Okay, but take a snapshot if you want. And questions and comments can be made through all three of these things. Olga's out today. Joe's going to collate all the questions. All right, and then just a heads up about next week, Yu Feng will be speaking. All right, without further ado, take it away, Diego.
Thank you. I'm just double checking here. Can you see my screen?
Mm-hmm.
Okay, perfect. So good morning, everyone. Thank you for hosting me today. I'm going to talk about my research on logically consistent language models using Neuro-Symbolic integration. I'd like to thank, first of all, Professors Antonio Vergari and Stefano Teso, who supervised me in this research journey, along with colleagues, fellow students, Karim Lorenzo and Emil, who contributed to this work through the research in this line and within the lab. My work has been conducted in between two labs, one during my master's studies at the University of Trento with Stefano, and then the April lab led by Professor Antonio Vergari in the University of Edinburgh. You can find more information about this project in the implementation and related works on the website. So I'm going to talk about deep generative models in the context of probabilistic reasoning and logic reasoning. That is, how it is possible to provide guarantees in order to have flexible but also reliable deep generative models. So deep generative models nowadays, recognized mostly as large language models for natural language processing and vision, are now scaled models with millions or billions of parameters that can capture complex multimodal distributions with different semantics. And progress in also in engineering made it possible for these models to model the distribution of internet-scale data. However, these are still probabilistic models and mostly reason in terms of soft constraints. So in the context of safety, for instance, discouraging a certain behavior, aligning the model away from some undesired outcomes consists mostly in minimizing the probability of such outcomes to appear. While this does not always necessarily translate into guarantees in case of hard constraints, and there's a variety of applications in which the respect of hard constraints is necessary. We can think about mathematical reasoning and logical deduction in the context of proving theorems, thus having a sound logical inference procedure with these models. And we have seen recent work with foundation models such as DeepSeek Prover, for instance, that feature a complete LLM training pipeline end-to-end, where a logical solver and exact solver is involved, but in the verification state. So we're talking about, for instance, RL with verifiable rewords. So despite this model is being aligned and compared against an exact logic solver, we still see marginal improvements, and in novel benchmarks such as the Math Olympics or Prover Bench still see a considerable amount of failure cases. We also have molecular reasoning, in this case, the prediction of chemical reactions, which is one of the big problems in computational biology. That is crafting molecules that are synthesizable through known chemical and predictable chemical reactions by using also building blocks that are accessible in order to have actually synthesizable molecules starting from virtual screening. In a context of AI safety, for instance, scene understanding in the context of autonomous driving, and the possibility to encode hard constraints with human rules. Our starting point was the problem of logical inconsistency in language models. that takes as example task question answering. So these two were the works that lay down the foundations for our experimental setup, starting from this work from Eric Mitchell et al. in Christopher Manning's lab, where, first of all, they queried the knowledge of language models and analyzed it in terms of factuality. So what is the level of truthfulness of the knowledge that the model encodes? And measuring types of consistencies between different facts, different atomic pieces of knowledge within the language model. And similarly also to language models with rationality, these in this inference pipelines, we have at first a deep generative model, a language model from which we elicitate, distill knowledge and beliefs about facts. And then given a reference knowledge base, given some reference constraints, logical constraints, we verify the consistency of such knowledge inside the LLMs by using by adding on top logical solvers. So in this case, we have an external logical solver added to the inference at inference time to the pipeline to assist a language model. And these works found that language models not necessarily, despite they encode factual information, not necessarily such factual information is consistent with itself. More recently, we have seen works this year and the past year in the context of reasoning models. This new wave of language models fine-tuned with RL for long reasoning traces to solve coding or math problems, for instance. And still we see works that look into the failure cases. So, for instance, cases of reward hacking, where the chain of thought does not necessarily represent or justify the final response, and there are some features that are exploited by the LLM to provide certain outputs. Or the case of controllability of chain of thought. So cases in which the LLM can get stuck in its own reasoning or be biased with its firstly generated solutions and actually, for instance, getting stuck in tuning its own outputs without actually branching out, without performing a proper search. Or we have an analysis, for instance, in the inductive or deductive reasoning capabilities of language models, where specifically in deductive reasoning seem to fall short, depending on the evaluation. So we start with the goal: how can we have deep generative models, neural networks, reason with hard constraints, symbolic constraints in a reliable and efficient way? So our work, our full paper embeds the experimentation also done with the workshop paper with some preceding work in which we first started looking into one type of logical consistency and factuality in small language models. And then we extended this to slightly larger open source models across different types of logical consistencies. So here we start with the definition of logical consistency with three fundamental logical rules that are at the base of logical reasoning for propositional and first order logic. We have, first of all, forward implication, which is by considering two logical variables, each one encoding and one atomic fact. A forward implication consists then in A implying B or not B. And here is an example where we have, for instance, an entity, albatross, and a relationship and a property. So albatross is a bird. That implies that albatross is not, for instance, a fish, according to a given knowledge base. Then we have the reverse implication, which similarly has a premise, which is actually a negated fact, implying the negation of another fact. So albatross not being an organism, implying that is not a living thing, for instance. And negation consistency, a type of logical consistency that we have seen also in other works, such as discovering latent knowledge, eliciting latent knowledge, and also the works that I previously mentioned. In this case, simply, we don't want a language model to contradict itself. That is, stating a fact and stating at the same time a semantically opposite fact, which is not just the logical negation or the opposite probability. And in our work, we show how, starting from, for instance, a Llama 2 model, actually, this model can present inconsistencies by replying, by assigning truth labels to such atomic pieces of knowledge inconsistently according to these constraints. We have some issues initially to enforce such logical constraints in language models. First of all, we need a single framework, a unified framework, a language to represent different instances of logical constraints, so implications, negations, but also account for quantifiers. Then we need a way to embed these such hard constraints in possible assignments that satisfy these constraints in probabilistic models. And considering the fact that logical constraints are piecewise constant functions, despite being almost differentiable with no gradient information. So initially, let's define types of logical consistencies. We have factuality. So one logical variable represents, encodes one fact, an atomic piece of knowledge. And in a language model, we can distill a truth assignment by considering the fact as a string that is condition. And we know the language models basically encode sequences of tokens and condition probabilities of tokens to follow up in the sequence. And thus we can see that a truth assignment can be the probability of a set of positive tokens, affirmative statement tokens that follow a question or a statement. For instance, if we query the LLM, is an albatross a bird? We are querying the knowledge, the truthfulness about this fact from the LLM, and thus the probability, the aggregated probability actually among positive labels, L true, is the probability of the fact. Second type of, so with factuality, we mean in this case, whether the knowledge distilled from the LLM matches then some ground truth labels, an external knowledge base of facts. In the case of negation consistency, we have two facts, two pieces of knowledge, where one is the semantic opposite of the other. So it's not necessarily the logical negation or the opposite probability. And here we encode this constraint as the XOR constraint. That is, given two logical variables, only one can be true. Then we have the logical implication. That is, with two logical variables, one implies the other, which translates in not A or B. So we can see that here either both cases can be true, or that the second variable can be true, or both negated. So we're going to evaluate this, especially in the case in which we have true premises, and thus look into what are the implications. And similarly, for reverse implication, we start from a premise that is actually negated semantically, and see thus, for instance, what a negated fact implies. Then we're going to look into more complex constraints. So starting from these simple logical rules, we can see compositions. We can see trees of entailments. For instance, here we have an atomic facts, so pieces of factual knowledge, ZF1, ZF4, combined with, first of all, an implication, and we have here a nested implication. And this is a visualized sample from entailment banks. So here we can, for instance, infer knowledge about the process of melting of ice, and an observation, the mass of the ice will not change, by starting from some atomic facts. So melting is a kind of phase change, and phase changes do not change mass. And thus, since we have satisfied these implications, we can derive the final conclusion: the mass of the ice will not change. This setup, specifically to the second paper that we mentioned, language models and irrationality, is particularly useful to assess the knowledge and to verify answers from language models in question answering setups. So how do we enforce such constraints? We consider K to be a logical constraint to be satisfied, and we want to maximize the probability according to the possible truth assignments in this deep generative models to satisfy the constraint. From an optimization perspective, we want to minimize a loss, that is the negative log likelihood of satisfying such constraint. The probability, according to a deep generative model with parameters theta, of satisfying a constraint given a truth assignment z, where z is indeed in a context of assignments sampled from the language model itself, is in this case the expectation over possible assignments that these will satisfy the constraint. And this expectation corresponds to weighted model counting. That is, if we consider all the possible truth assignments for the variables that compose this constraint, we consider the probability of each assignment, and the probability of each assignment if we make the independent assumption of the variables. So for each truth assignment that covers multiple single atomic fact labels, that is different logical variables that constitute the assignment, we assume these to be independent, and for each one, as shown previously, we query the probability for a truth assignment for each logical variable, and thus, according to the truth assignment, we're going to consider either the probability of Zi or the opposite probability when the assignment is negative, is 0. However, computing weight model counting, that is enumerating all the possible words satisfying a constraint in order to compute their probabilities, is hard, and it's hard to compute in general. So how can we encode this constraint and possible word assignments in a tractable way? We can use a generalization that is probabilistic circuits, and this work features a first instance, a specific case of probabilistic circuits. That is, we can basically break down a logical constraint into a conjunction normal form, for instance, and then consider its probabilities, the probability of the single variables, and compiling them in a probabilistic circuit. That is, when we start, for instance, with constraint k with logical variables y, 1, 2, and 3, we consider the possible assignments. We have here a conjunction between two implications. And if we start breaking it down and bring it into conjunction normal form, we start basically seeing the conjunctions as multiplication of probabilities and the OR operators as summation of probabilities. And eventually, by enrolling this constraint, we end up with an expression in terms of probability of single logical variables that compose this constraint. That is a probabilistic circuit, a computational graph. So by compiling a constraint into a probabilistic circuit, we can compute weighted model counting in a constant time. And this is initially we prototyped this computational graph by using sequential diffusion diagrams that allow to compute weighted model counting and compute the possible words efficiently. And eventually we abstracted and developed a framework called Circuit that I invite you to check for other applications also in related works in Okay, I think there was for a moment a connection issues. Connection issues should be fine now. So in the context of the semantic loss within this framework, we start from a logical constraint that we want to enforce. We compile it into a probabilistic circuit. And since we have now, we have computed efficiently the possible assignments, we compile this into the semantic loss. That is, given this probabilistic circuit, this computational graph of probabilities, we want to minimize the negative log likelihood. And this can be done eventually end-to-end and we can train thus a model, the model with whose parameters are used to compute such probabilities end-to-end with stochastic gradient descent. So in our experimental setup, we consider two databases. First of all, we start with Belief Bank, which is a subset of ConceptNet, which is a knowledge base handcrafted by humans with knowledge about different entities and properties of these entities and logical relationships between these. So implications, XOR negations, or reverse implications, for instance. They consist of two splits. We have thousands or tens of thousands, respectively, of training and test samples on different entities that have similarities, but they belong basically to two different domains. And this corresponds to eventually about 1,000 of abstract logical constraints. And if we combine this with the available entities for respectively training and test set, we eventually have about tens of thousands of ground logical constraints that we convert into propositional logic. The goal here is to consider, first of all, as a baseline, a model that is trained on all factual knowledge belonging to this data set. So a supervised fine-tuning model baseline compared to a model trained with the semantic loss. And the question is, given that we have access only to the premises of these constraints, given that we only have access to the antecedents, so we know what are the starting point, what of these logical implications, we evaluate the model on the consequence, that is, leveraging the constraints and the premises to predict, to infer knowledge about the consequence. We extend the setup then to entailment bank when we don't look only at one hop logical implications, but also d-depth hops logical implications, so trees of entailments through the entailment bank dataset. For evaluation, we're going to quantify factuality in terms of F1 score. So we are considering this as a classification setup for in order to classify whether a fact is a true or false according to the language model and compare it with the ground knowledge in these data sets. And then we're going to quantify implication or reverse implication as the 1 minus the fraction of violated implications. That is, if we look at the constraints, for instance, in this illustration, we look at all the constraints where the premise is true, and we thus look into the implication, the consequent, whether this matches the logical constraint, and we look thus for the opposite fraction of violations. Same thing for the negative. For the negation constraint, we look at all the cases in which, for each statement, the model does not assign a true label to its semantic negation. So we considered first a bunch of baselines. Again, the plus cross entropy, that is the model Llama 2 7 billion fine-tuned on all the factual knowledge in the training set of the leaf bank, but also we assess the knowledge zero shot, few shot, and chain of thought of the Llama 2 7 billion and 70 billion models. And here we also quantify the perplexity, especially in the context of fine-tuning. That is the second section of this table. We quantify perplexity in order to measure the shift from initial distribution of the language model once we apply these hard constraint rules through the semantic loss. And we can see how in factuality, generally, all models improve, especially in the case of forward implication and negation consistency. We're over some of the baselines, and especially the supervised fine-tuning the baseline. And we can also see here a diagonal trend in which, when we consider a language model fine-tuned for a single specific logical constraint rule, so negation consistency, for instance, the model is overall the most consistent with respect to the baseline and the other fine-tuned models. And the same applies for forward implication. And then we have the super model, in which we fine-tune this language model on all the logical constraint rules that we have considered. So factuality, logical forward implication, reverse implication, and negation constraint. So we also make a distinction here between consistency and self-consistency. That is, when we evaluate the implication and the reverse implications and negations, we take into consideration only those constraints where the premise is true according to the language model's own beliefs. While with consistency, not self-consistency, we consider all the constraints where the premises are true according to a ground truth label. according to an external knowledge base. And I'm going to expand on self-consistency in short. When we consider then forward implications, entailments that are farther than just one hop, so deeper entailment trees, again, we consider the entailment bank data set with about less than 1,000 test samples. And here we evaluate our models in transferring basically from knowledge in belief bank in the training phase, with which comprehends a set of entities, a variety of entities that hopefully could transfer to other knowledge bases. In this case, for entailment bank. So we evaluated especially our model trained on negation consistency, forward implication, and consistency on all the logical constraints, and consider as baseline zero-shot llama 2 7 billion. And we can see clearly that the llama 2 baseline decreases in implication consistency as we increase the depth of these entailment trees. That is, for each sample, we basically increase the amount of facts that we're going to verify in logical constraints. And we see that the highest consistency that also maintains constant is the case of the forward implication model, which is trained specifically for such implication constraints. While overall, also the model trained for reverse consistency, reverse implications, and negation consistency maintains a constant but still inferior accuracy score. So we achieved, basically, we managed to obtain a training procedure that allows to increase the consistency of logical consistency of language models with respect to some hard constraints. But there are some assumptions. In this case, we assume that the variables constituting the word assignment and satisfying these constraints are independent. And we don't have necessarily guarantees at test time when we sample eventually from this fine-tuned language model. We distill some knowledge and we perform logical inference. We have no clear guarantees. So there's further work from the April lab that featured basically architectural modifications such as semantic probabilistic layers that allowed also at inference time to enforce the respect of hard constraints with deep generative models. And I suggest to look into this work in case you're interested, especially in at test time. We can see here different instances also of semantic probabilistic logical layers, for instance, with tractable control. So in applying control techniques in autoregressive models for text generation. Similarly, these are alternative forms. And safe reinforcement learning. So here there's an intersection with reinforcement learning for neural networks, but also language models. So future directions on this work. We firstly discuss the problem of factuality. In our setup, we considered an external knowledge base with human handcrafted annotated labels. And another source of factual knowledge could be retrieval systems. So in language models, in natural language processing, we have seen retrieval augmented generation, RAG, and we're discussing possible ways to augment to provide ground truth and scale also the size of these data sets of ground truth labels for our factual consistency constraint through retrieval systems. Moreover, I previously mentioned self-consistency, and enforcing logical consistency in language model can be done with our method with respect to a provided knowledge base, where we have factual knowledge and given also logical constraints. But other works, such as this work from Ekina Kurek in Jakob Andres' lab, looked into the deductive closure training of language models, where with deductive closure, we mean the space of logical variables, facts that are inferred, that are deduced from the language model, by starting from a set of constraints and initial knowledge. So this is a way for the language model to expand basically the knowledge base with respect to its own knowledge, to its own belief. And if we generate trees of entailments and we basically generate synthetic knowledge graphs and apply the semantic loss on it, which is part of the current experiments. We can assess whether a language model, whether it's possible to ensure self-consistency on larger trees of entailments on such language models. And this could be a form of self-supervised logical consistency training. Eventually, we evaluated our models and our methodology on single-shot question answering, but by expanding also to trees of entailments and self-supervised logical consistency training, we plan on evaluating these models in question answering tasks, where originally similar to some works from which we considered as reference, we can verify the answers of language models through techniques such as backward chaining or forward chaining. So I think, I think I went pretty fast over the slides, but this is the end of my presentation, and I thank you for the attention. And if there are any questions, I'm available also to clarify about possible sections of the papers. So thank you everyone.
Okay, great. Thanks so much, Diego. I don't know if this has ever happened to us before. Somebody actually being more efficient than normal. So thanks for that. So, all right, we have some questions from Discord. Dominica, the word ice in natural language refers specifically, therefore the sentence, melting does not change the weight of the ice is not true, contradicting what is implied by your constraints. Do you take into account this additional difficulty coming from the effect of counterfactuality when assessing the model's performance?
Could you clarify the question initially? What do you mean here with counterfactuals in this trees of entailments?
Ken, maybe you can put this question on the screen.
Mm-hmm.
Oh, we can't do it for Discord questions. Okay, let me read it again. I think there's a typo in here. The word ice in natural language refers specifically to water in solid state. Therefore, the sentence, melting does not change the weight of the ice, is not true, contradicting what is implied by your constraints. Do you take into account this additional difficulty coming from the effect of counterfactuality when assessing the model's performance?
I guess, okay, my understanding is that there are two possible problems. One is the ambiguity in the semantics of such statements. And this is because also natural language is intrinsically ambiguous. And what we do is when we assess query the knowledge of these language models is averaging through different formats for the same prompt in order to, and we average across different formats, different prompts of the queries to assess ambiguity and noise over prompts, which is shown to be present for LLMs. And also, it is possible, and we observed this through training, to collapse into trivial solutions. For instance, implications can be satisfied by assuming that all the variables are false. And so in this case, this is a reasoning shortcut, what we define reasoning shortcut or case of collapse to trivial solution that can only be tackled when we have also factual ground truth labels that we can combine. So in this case, like training on entailments, training on these nested implications required also enforcing the factuality constraint. And probably this connects more to the question. You need some partial ground truth knowledge to start from in order to then apply these logical constraints.
Mm-hmm. Okay, great. Question from Procor. Did you ever consider such a logical constraint circuit, in quotes, for logit selection?
For logit selection,
Mm-hmm.
I think this is connected with one of the last papers that I mentioned. I suggest to look into this article in case you don't know it already. Yes, this is a form of decode. It's a decoding strategy, but this is applied at test time, or basically, yeah, at inference time. You can sample using different decoding techniques from a language model, but at training time, we were interested more in basically developing a knowledge editing technique in making sure that in modifying the knowledge language models to make them make it more consistent. So I maybe I don't know if this completely answers the question, but we should make a distinction then between training or techniques at train time or test time.
Okay, great. Also from Procor, how well does the model circuit generation scale? How fast can it be, rendering the whole adaptable?
So we found, so compiling a probabilistic circuit and computing, so once we have compiled each constraint into a probabilistic circuit, we can just we can just compute it once and plug it to the loss, and it is much faster than running a SAT solver on top of the LLM labels every time we are querying a specific logical constraint. So this can be done once and enforced. The one challenge in scaling surely is expanding, so considering more complex logical constraints. Here, trees of entailments. I have the visualization in here. So especially if we were to generate knowledge graphs from the LLM and consider a very long reasoning chain, yes, we would start decomposing this basically into single implications with multiple hops and increasing depths. Surely, further work should feature a scaling analysis and the size of the model, and also the depth of these entailments. But from what we could see in our experiments, it's still possible at this scale with this with a fixed amount of compute, the same that we used for single hop constraints. Again, you amortize basically the cost of compiling, of performing weighted model counting, and compiling the probabilistic circuit once, and then train on it.
Okay, great. From Resident, does the use of ConceptNet, is it obligatory to get the thrust?
Sorry, I didn't understand the last part, if it's a bit obligatory.
Not sure I do either. It's sort of a typo. Does the use of ConceptNet is obligatory to get the thrust?
I'm not sure what they mean with thrust in this case, but ConceptNet, we adopted ConceptNet because this was the benchmark, the reference data set from these previous works that I mentioned. So we needed to develop a technique that was comparable with existing methods, especially based on solvers. But I suggest to look actually to the work of Stefano Teso from my lab at the University of Trento. They developed a benchmark on reasoning shortcuts and expand to other data sets. ConceptNet is not a very large scale knowledge base, but it was definitely a good reference, good enough for our experiments.
All right. Regarding the first question about ice, could word embedding solve the ground truth table problem?
I see. So consider, I guess, whether vector arithmetics could be used to satisfy. I think rather than considering this as a method to apply a priori, I would consider it as an a posteriori evaluation to look into how word embeddings change when you enforce these consistencies. I mean, word embedding, I think that if you mean with word embeddings the evaluating the probability of some concepts, of some representations to satisfy the constraints, it is what we do fundamentally. The logits that we normalize and turn into probabilities in a language model are represent, I mean, are correspond to the embeddings for a specific fact. So here you could take, I'm going to the slide. Okay, here at the bottom, this xt, which is the true assignment label for a conditioning statement, this can be seen as the embedding of zf equal to true. We did an analysis on word embeddings. I mean, in the appendix, you will find a table with pairwise similarities between the embeddings of the training set and the test set, which suggests that there is a motivation for which this model can transfer once it's trained on one domain of entities, it can transfer to similar entities. And so we can see the same consistencies and for the same properties when we have similar entities. Yeah.
Okay, great. From Michael Whitbrock. Hey, Michael. This technique seems fairly bound to propositional logic. Is the only way to first order or higher order logic via this sort of grounding? If so, is the sort of grounding search used for? For example, is Markov logic a way forward?
I'm not sure about the application of Markov logic, and it depends, I guess, on the setup and what kind of logical consistencies you want to apply. And regarding grounding such logical constraints, I think connecting also to the previous question, it is interesting to see. I mean, the problem in first order logic is solving, in this case, quantifiers, and from my experience, and so you would need to translate a universally quantified logical constraint into probabilities and facts that on which this constraint is grounded. So this is one way for us when we compile manually, given a knowledge base, these abstract universally quantified constraints into entities. But this could also come for free for similar entities as we suggest in our analysis. So if you have a subset of grounded logical constraints for some entities, you can start looking at the neighborhood from an embedding in embedding space. So semantically similar concepts. And again, you can query the properties and see if there's some level of transfer. And this could imply that you have a level of quantification within a subspace of the representation space for that specific logical constraint. That could be an analysis, a follow-up analysis to this work.
Okay, great. From LinkedIn, Benjamin Perez. This might be a naive question from someone coming from logic, but I couldn't quite understand the difference between factual propositions and the variable z, especially when it comes to distinguishing factual negation from the negation of z. I understand that one of them is soft and the other is classical.
Okay. On this, so z for a specific atomic fact represents the variable for in the context of that specific fact f when we have a truth assignment. And so here in this slide, f corresponds to the statement albatross is a bird, and Z is the corresponding assignment to the statement. But when you consider not F or 1 minus probability of ZF equal to true, you're basically considering generally any other fact that negates semantically any other statement that negates this this fact. But so basically you're taking 1 minus p from the perspective of the deep generative model. You're considering 1 minus p ZF equal to true, but P itself is a very small probability specific to this context, to the sequence, and 1 minus P is very large. But you're not fully capturing, you're not capturing a specific semantic negation. You're capturing basically from the language model point of view any other representation as opposed to the one that we're querying. So this is why we consider as negation the semantically opposite concepts as basically separate facts. So we negate this piece of atomic knowledge semantically and consider this as a separate fact that will be, though, the opposite of our first one, F1. So I don't know if it's clear, but I'll be happy to clarify this maybe with the paper as reference.
Okay. From YouTube, is this Alex Segal? Is this generalizable, or does it relate to Markov logic networks by Pedro Domingos?
Okay, I'm not fully familiar with Markov logic networks, so I would have to read the paper and try to draw a comparison. But in terms of generalizability, I can tell that, I mean, we talked about scale, and we talked about extending the setup, so training and evaluation. In terms of training, I believe it's possible to scale this method by considering we don't need necessarily annotated knowledge bases, but we can look into now knowledge bases generated by the LLMs, so we can shift our attention into self-consistency. Once we basically disentangle and consider the problem of factuality as grounding, for instance, with a retrieval system, and then enforcing self-consistency of the model with their own reasonings, I think this is possible. While in terms of scale, yet I mean, further work should indeed feature like testing, training on larger models, and parallelizing also. I mean, this is a negative log likelihood loss from an engineeristic perspective. I mean, you can distribute a model and aggregate gradients across multiple GPUs. So technically, training is scalable, but yeah, we leave this to future works.
Okay. Since also from Benjamin, since there is a broad literature arguing that neurosymbolic approaches offer greater transparency, how do you see the relationship between neurosymbolic logical consistency and that broader transparency project?
So neurosymbolic consistency in these language models, the point here that we make is looking into the knowledge that the language model has. And with logic consistency, we take some logical constraints as reference, and we want to make sure that the knowledge of the LLM is coherent with such constraints, with such knowledge graphs that we crafted. So I think from this point of view, and maybe I'll need a clarification on this question, but I believe that with transparency, if we want the language model to adhere to some specific logical relationships, to some specific representations of knowledge, this is a way to enforce it. And there's a clear technique to query, first of all the elements composing this knowledge graph, so atomic pieces of knowledge, atomic facts, and then query the relationships. But yeah.
Okay, clarification from Michael Whitbrock. Sorry about the editing problems with my question. I didn't mean specifically Markov logic. I meant the grounding search that is used for estimating probabilities of Markov logic. I think this is about grounding.
I see. I should look more into Markov logic. I'm sorry, I'm not really familiar with that. So I can explain more how we perform grounding in our case for our constraints. Also, I invite to contact me over email. Otherwise,
Maybe say a little bit about your grounding.
yeah. So our starting data set consisted, so you can basically have more abstract logical rules, which are in first order logic, you have a quantifier and general variables, and you instantiate it by considering when you have, on the other hand, a set of factual of truth assignments, ground truth assignments for some facts, for some variables. You can, for instance, in the case of implications, you look at the premises of these abstract constraints and you check if there are instances for these premises where the ground truth label is true, and thus for the case of albatross, that respects a premise, for instance, is a bird, and you look at the abstract logical rule, a bird implies it's a living thing, then you can instantiate, you can perform the grounding and say an albatross is a bird, and since an albatross is a bird, you can imply that an albatross is a living thing. So for us, performing this grounding required, again, intersecting abstract logical rules with factual knowledge, so ground truth labels about the premises. And then our first analysis, based on ablating the implications, the consequence, and taking only the premises and the constraints, and see if the language model could learn correctly the implications, so the consequence.
Okay. Provided you solve the entailment tree problem, do you think there will still be a granularity problem? For example, 2 arms, 2 legs, and a head versus 1 human individual?
I believe it's possible. I mean, I think this touches the field of mechanistic interpretability in language models, and how consistent are representations, if you look at compositionality in language models. And on this, I suggest to read more into the literature from Brown University and Eli Pavlik, if I'm not wrong. So it's possible. You can have such problem of consistency. And there was another point I was trying to remember. Yeah, and also another line of literature that I suggest looking into. So what we discussed so far is the knowledge editing technique. We can assume, we solve these entailment trees. We enforce constraints according to these entailment trees in the language model, with some facts according to some domain. But since we're editing, we're modifying the log likelihood of specific facts in the language model. This can have some side effects, which are called ripple effects of knowledge editing. And on this, I suggest looking into the literature of Morjeba at Google. It's called the ripple effects of knowledge editing. So this is another possible side effect to look into. And we try to estimate a possible ripple effect by just looking at the perplexity on one of the pre-training data sets. But another possible future analysis should be measuring the consistency for other sets.
Okay, great. We have a few more questions, but just in case anybody will be leaving at the hour, let me just mention we had 2 fun things just happen. We just passed 2,000 users on Discord, and we hit the super lucky number 888, the luckiest number in China, I'm told, on YouTube. All right. So we will celebrate that. Okay, question. could you please connect this to ELK, eliciting latent knowledge research? For example, deducing latent explanations of statements with probabilities.
So ELK is, and from this project started as I was reading about ELK, and especially discovering latent knowledge, the work from Jakob Steinhardt's lab before ELK. And if I recall correctly, in ELK, they basically extended discovering latent knowledge by composing multiple, by probing the LLM according to some truthful features and imposing an orthogonality constraint. And such truthful features are indeed different types. We can see this as different types of consistencies. And in discovering latent knowledge, in the original paper, there was indeed one type of consistency, which is the negation consistency, which is pretty close to what we enforced in what we included in our work. So I started from that point, and I realized that negation consistency is one type of logical constraint, while by looking into semantic probabilistic layers from Antonio's lab, he was enforcing this type of consistency at inference time by adding this extra layer on top of neural networks. So then I started thinking about a training procedure that could instill this a generalization, basically, of the negation consistency and the specific learning rule proposed in discovering latent knowledge. And we came up with this framework that allows basically to plug in any logical constraint and deriving computing a loss on the fly for it.
All right. Is there a generalization from this to statements in semi-formal natural language? The circuit formulation seems to make it difficult by relying on hard constraints, but do you think that there is a way to represent probabilistic constraints?
Could you repeat the first part of the question? It was not quite clear to me.
Is there a generalization from this to statements in semi-formal natural language? The circuit formulation seems to make it difficult by relying on hard constraints, but do you think that there's a way to represent probabilistic constraints?
There's a line of works on formalization of natural language. In our work, we assume already a degree of formalization, and when you start from natural language, yeah, you have a decomposition into pairwise, like single hop logical rules and atomic facts, atomic piece, single variables. So yes, I mean, I suggest also looking into the line of research on provers and solvers paired with language models. So in the case of DeepSeek Prover, they have a formalizer component that transforms natural language into formal language, and then they apply on which they apply a solver. The problem here that you probably mentioned is the fact that formalization introduces some noise, introduces errors, and I think there's an intrinsic problem of converting natural language into formal languages, like in first order logic, translation, because language potentially is ambiguous.
Okay, great. Oops. We have a little glitch. Okay. From YouTube, I wonder if you looked into mechanistic interpretability, looking for mechanistic circuits that emerge in the process of your training.
We haven't analyzed circuits. We looked more into the representation learning here, so into the embeddings and how what was the relationship between the domains on which we enforced the logical consistency rules. But yeah, as I previously answered, surely future analysis should be also dedicated in how representations change with logical consistency, and yeah, also the emergence of circuits. But yeah, we We were not focusing on mech-interp.
Great. Would RASP/tracer program be able to consistently express logical rules?
Um, I'm not familiar with Tracer. I remember, yeah, I looked into some works that we referenced involving RASP. I mean, our logical rules that we consider in this work are quite simple. So they could also represent it, for instance, with deep problog. But I'm not sure about the scaling to trees of entailments. Yeah,
Okay, great. All right, you can see you got quite a few questions, Diego. So
I'm glad.
very enthusiastic um, group here around your work. Oh, one more question. Uh, maybe similar to the entailment tree problem, do you see any way to enforce hard constraints in a certain sequential order?
I'm not sure I correctly interpret in a sequential order. If you mean, for instance, linear temporal logic or nested entailments. I mean, entailment trees could also be just a single sequence of entailments, nested entailments, or in case of linear temporal logic, yes. We were already considering this in reinforcement learning in markup decision processes. And for that, I suggest to look into the literature in reward machines. And yeah, in this case, logical consistency could be extended to the reward design. A reward function, a stateful reward function could encode linear temporal logic constraints, which is actually part of my current work.
Okay, great. Let me ask a few questions. Just for clarification, you began by listing issues of some overall issues, single language or framework, ability to combine soft and hard constraints, and weak gradients. So the latter two I want to ask about. So when you say soft constraints, what exactly do you mean? Do you just mean constraints that hold with some probability, which you mentioned, or any other sense of soft constraints?
Yeah, exactly here, probabilities quantified then as, constraints quantified here are probabilities. So from the perspective of a language model, when we have in alignment, basically when we have some outcomes, in this case, it could be also some factual knowledge, some entailments, or a trajectory of which we want to minimize, for which we want to minimize the probability. And this is the way constraints are currently either reinforced or discouraged in language model training. Yeah.
Okay. And this third point, can you elaborate a bit on how you effectively treat this issue?
So here, logical constraints, in logical constraints, basically, when we compile into a probabilistic circuit a logical constraint, we have we decompose this into a series of truth assignments. When we perform weighted model counting on a constraint, we obtain different sets of probably this is a better visualization. We obtain different sets of word assignments Z that satisfy the constraint, and these are different possible assignments for these atomic facts. So the problem here is enumerating and combining these probabilities. So here we have a summation. Weighted model counting basically produces all the possible words, all the possible sets of assignments that satisfy the constraint. And here, when we perform, when we increase our likelihood, when we enforce basically the LLM to converge to one or a subset of these assignments, we are framing this as minimizing, optimizing the negative log likelihood. And this is also the core of the problem in terms of computation of these assignments that is performing weighted model counting. And this is why we propose this method. So we propose involving probabilistic reasoning. And this also connects to one previous question. Here, there's still a problem of collapse into trivial solutions, so reasoning shortcuts, even in this way, because constraints can be satisfied, in this case, implications with some trivial assignments. So for instance, all false, all zero. So while this makes sense logically, it does not if we consider some ground knowledge. So this then basically, encouraged us into combining, considering multiple logical constraints at once.
Okay, great. Well, lots of interest in your work, Diego. So if you can, maybe jump on Discord if in case there's anything we didn't address. Ken, can you put the Discord link in the Restream chat just to make it easy for you to access Diego? But all right, thank you so much. And everyone, just because it's getting close, reminder that our big signature event, the summer school, is coming up in August. So mark your calendars. We have the dates on Discord. Oh, there you go. There's the link, Diego. All right. Well, thanks, everyone. I think we'll do an in-between today, between our long format and our new short format. We'll end a little bit early. Thanks so much, Diego.
Thanks, everyone. Thanks for the interest.
All right. Take care, everyone.
Bye.